Jai Hind. Welcome to the course Network Analysis and Synthesis, and I am going to discuss today one of the network theorems, that is Millman'S theorem. First we will discuss what is Millman'S theorem, its statement and then proof, and we will carry out some examples using the Millman'S theorem. So, Millman'S theorem states that if the network containing a large number of energy sources, the energy sources can be voltage or current, with their series impedances can be replaced by a simple network containing a voltage source equivalent in series with an equivalent impedance. And this equivalent voltage and equivalent impedance can be given by this empirical relations. So, we can see that if the network containing n voltage sources, say E1, E2, E3, En, with their series impedances, say Z1, Z2, Z3, Zn respectively, then the network can be replaced by a simple network containing a single voltage source in series with an impedance Z, and the value of this E and Z will be given by these expressions, where E is E1 Y1 plus E2 Y2 plus En Yn divided by Y1 and Y1 plus Y2 plus Y3. So, Z1 is impedance, so Y1 is admittance, Y1 is 1 by Z1, that is admittance. So, if simplified, it will come voltage, and Z is given by 1 by Y1 plus Y2 plus Y3 plus Yn. So, this way, if a network is containing n number of voltage sources with their series impedances can be replaced by a simple network containing a voltage source E in series with an impedance Z, and the value of E and Z can be calculated by using these relationships. So, we can see here this is a network containing n number of voltage sources with their series impedances can be replaced by a simple network containing a voltage source V in series with an impedance, and these V and Z can be calculated by using this relationship. The dual is also true. The dual is also true means if a network containing n current sources, say I1, I2, I3, In, with their admittances in parallel, say Y1, Y2, Y3, Yn, then the network can be replaced by a simple network containing a current source I in parallel with an admittance Y. So, dual is also true. So, we can, this is the, so this is also true, this is also true. So, if the energy sources can be voltage source, can be current source. In case of the voltage source, we simplify in this way. In the case of the current source, we carry out this way. So, I1, I2, I3. So, it can be replaced by a simple current source I, and this is the Y. And this I and Y can be given by this. This I can be this is the I and this is the Y. So, n current sources having the magnitude I1, I2, In in parallel with admittance Y1, I2, Y3 can be replaced by this simple network I and Y, and I and Y can be calculated by using these two equations. The proof is very simple. The proof is very simple of the Millman'S theorem. So, I can do the proof here. So, proof is not, so proof. Say this is your These are the two terminals, say this is A and B, AB. So, this is your E1, this is your Z1, this is your E2, this is your Z2, and this is your En, Zn. So, this between terminals A and B, there are n number of energy sources with their series impedances, they are connected. So, this can be so simple, it can be written as like this. So, this is your say this is your I1, this is your Y1. Similarly, we can write this. So, this is your I2, this is your Y2. This can be written simple source transformation Yn, and this is your In, and these are the two terminals, say this is A and B, A and B. So, what I have done, just source transformation of this voltage source with impedance. So, this is the current and this is the admittance, current and admittance can be written as, this can be written as a simple current source, say this is your I, because all the currents are approaching terminal B. So, I1 plus I2 plus In, and all the admittances are in parallel. So, they can be added like this. So, this is Y, this is your A, this is your B. So, I is equal to I1 plus I2 plus I3 plus In, and admittances are in parallel. So, they can be added. So, this can be converted into a simple voltage source in series with an impedance Z. So, this is E and this is terminal A and B. So, proof is very simple. Proof is very simple. Converted into current source, then addition of all the currents are approaching terminal B. So, I1 plus I2 plus In is equal to I, and all the admittances are in parallel. So, they can be added. So, I is equal to Y is equal to Y1 plus Y2. So, this is the proof of your Millman'S theorem. So, proof is very simple. Now, we will carry out some examples. So, solve the circuit shown below using Millman'S theorem. So, circuit is like this, it is like this. This is your and this is your one energy source, there is another energy source. So, E1 is given by 20 angle 0 degree volt, and this is 1 plus J1 ohm, and this is 1 plus J2 ohm, and this is 1 minus J1 ohm, and this voltage source is of 20 angle minus 60 degree volt. This is the terminal of the network A and B. So, find the current through AB branch impedance say 1 plus J2 ohm. So, this is the problem using the Millman'S theorem. So, what you have to do is we can see here the E1 is angle 0 degree volt, Z1 is 1 plus J1 ohm. So we can find out Y1 is equal to 1 by Z1, because this circuit can be transformed into like this. This is your voltage, this is your impedance, and this is your, you have to convert this circuit into this fashion. Okay, so this is your E and this is your Z, and this is your A and this is your B. So it is 1 plus J2 ohm. Okay, so E2 is 20 angle minus 60 degree volt, and Z2 is 1 minus J1 ohm. So we can get Y2 1 by Z2. Then E is equal to E1 Y1 plus E2 Y2 upon Y1 plus Y2, and Z is 1 by Y1 plus Y2. So once we get this value of E and Z and putting here in this circuit, we can get the current through the 1 plus J ohm. So Y1 is coming, so I am just writing the straight way. I1 is 0.707 angle minus 45 degree. Z2 is 1 minus J1, so Y2 is 1 by Z2, so it is coming 707 angle 45 degree. Okay, so E dash is coming, or E is, if you putting in this value, it is coming like this, 23.66 minus J 13.66 volt, and Z is, so Z is coming this, it can be converted into rectangular. So in rectangular format it is coming 0.5 plus J, so plus J and minus J, so J 0.5 and 0.5 plus J 0.5, so it is coming 1 by 1, so it is coming 1, so this is, so 1, so it is coming 1 ohm. So we can get this E and we can get the Z, and then we can calculate the current using the Millman'S theorem. So I is coming, so straight we can write here I is equal to current through I is equal to 23.66 minus J 13.66 divided by 1 plus J2. So it is coming 23.66 J 13.66 upon 2 plus J2. So it is coming, you can check, this value is coming 9.66 angle 75 degree ampere. So the procedure is very simple. Convert the given network into Millman'S equivalent circuit having one voltage source E and in series with an impedance Z, and then add this impedance through which the current is required, and then you can find the current through this element. So this is the very, now one more problem I am just discussing here. This is we can have problem 1. In the network shown below, what load ZL will receive maximum power? And what is the value of maximum power? And what is the value of maximum power? So, similar type of problems we have carried out using the maximum power transfer theorem. So, this problem also can be solved using the Millman'S. So, circuit is like this, it is like this. This is 50 angle 0 degree, then there is one impedance 5 plus j5, then there is this is the ZL, this is your ZL, and then we have another impedance of this voltage source, it is 25 angle 90 degree, and this value is 3 minus j4. So, what is the ZL? ZL is the, what is ZL? So, ZL is the complex conjugate of Z. Okay. So, what you have to do? You have to find Z, and Z is nothing but it is y1 plus y2. Okay. So, first find Z from this circuit. Z1 is, this is the Z1, this is your Z1. So, this is your Z1, this is your Z2. So, we can find y1 is nothing but 1 by Z1 and y2 is 1 by Z2. So, we can find y1, y2, then take the take summation of this y1, y2 and take the reciprocal, that will give the Z. Once we get Z, we take the complex conjugate. So, this is coming. So, I am just writing a straight away. So, Z is coming, it is coming 4.24 minus J 1.8 ohm. Okay. So, ZL is, so we can write here for maximum power transfer, for maximum power transfer, this ZL is complex conjugate of this Z, which is 4.24 plus J 1.18 ohm. So, this is the value of ZL. Okay. Now, what is the maximum power, or P max is nothing but it is E square upon 4 RL. If you remember, in case of the maximum power transfer theorem, it was VTH square upon 4 RL. In case of P max is equal to VTH square upon 4 RL. So, what is this? This is the voltage across the terminal of the network. What is this? This is also the voltage across the terminal. So, 4 RL. So, E can be get, and E is equal to E1 Y1 plus E2 Y2 upon Y1 plus Y2. So, this is a very simple algorithm. So, here we can get E. So, E square upon 4 RL, and this is your RL plus J XL. So, this value we can take from here. So, it is coming E is coming like this. So, it value of E is 9.85 angle minus 78.99 volt, and P max is E square upon 4 RL. So 9.85 square into 4 into 4.24. So it is coming 5.72 watt. So this way we can carry out the Millman'S theorem. Procedure is very simple. What you have to do? You have to convert the complex network. This is your E1, this is your Z1, this is your Z2, and this is your Zn. Okay. So first convert it into this like this. So it is this is your E and this is your Z. So and then you can find this. So Millman'S theorem is very simple. Here we can add the Zn. Okay. So this is the current through Zl. So convert this circuit into this, and finally we can find the current through. So this is the algorithm is very simple. You have to convert the complex network into simple, having one energy source and one impedance in series. If the energy source is voltage, if the energy sources are current, then you have to find the equivalent current and equivalent admittance, and you have to construct the circuit in current in parallel with the admittance, and this way we can solve the problem. So this is all about your Millman'S theorem, one of the important theorem of network theorems. So we have discussed the Thevenin's, Norton, maximum power, reciprocity, compensation, and this theorem was left, so I just discussed here. So thank you very much. This is all about your theorems. So next lecture we will carry out some examples using these theorems. So Jai Hind, thank you.